So we were talking about transformations in non-eutectoid points and non-eutectoid compositions where we have a couple things that happen. At a given temperature, that means it's going to transform across multiple phases. And we're going to come back to that concept. So hypereutectoid composition, this is above the eutectoid composition. We get proeutectoid cementite, which is what this is, formed in the material. Bainite is a specific example of that we've touched on. So depending on the rate of cooling and what temperature it's held at, we can either form perlite or bainite. But in order to not form perlite, we have to get down below this threshold of about 540, 530, whatever this is, 540 C or so. We have to get below that in a fast enough time. So typically that's going to be a quenching type mechanism to form these harder grain structures. So there's also a microstructure called spheroidite, or spheroidite, rather. Spheroidite. Say that several times fast. It'll get you really into some neat parties. Iron carbide particles that have a ferrite matrix. So formation is a function of diffusion. You heat bainite or perlite at a temperature just below the eutectoid for a long time to get these. That drives the diffusion, allowing the kinetic energy for diffusion to happen. It's a reduction of the interfacial area, trying to get small droplets. It's the same kind of driving force, effectively, that makes water droplets and oil droplets coalesce together. If you mix up oil and water and you shake it vigorously, like in a vinaigrette dressing or something, it always separates again because it doesn't stay forcibly mixed. The droplets of the two phases that are similar are going to coalesce. So we can also start seeing martensite, and this is a really important material. So this is a non-equilibrium transformation product. It's face-centered cubic at the austenite phase. Martensite is body-centered, but it's tetragonal. So it's not body-centered cubic, it's body-centered tetragonal. That makes it able to form these sharp shards, and martensite is actually what gives us a hard cutting edge in tooling and materials. So these iron atoms and potential carbon atoms are visible. The martensite is below the perlite and bainite temperatures. So you have to quickly, in a matter of less than 10 seconds, really only a couple of seconds, transition from the austenite region above 727 down below the threshold of about 220 or so, down below 220 C, inside of a matter of a couple of seconds to form a large percentage of martensite. So this transformation from austenite in the stable phase to martensite is very rapid. It's diffusionless. Its transformation depends on the T to which it's rapidly cooled. So the exact temperature. So 90% martensite is very rapid cooling down below about 150 C. If you can reach from 800 to about 150 C in 1 second, that's what this is, 10 to the minus 1, 10 to the 0, which is 1, 10 to the 1, which is 10, 10 to the 2, 10 to the 3. So inside of 1 second, if you can drop all of that temperature, this is why water quenching is used to make cutting edges of things, not just oil quenches where you get into the sort of perlite bainite region. You get down into martensite. It's very rapid. It's very diffusionless. Slow cooling gets you to alpha, which is body-centered cubic, and cementite. Martensite is a single phase, body-centered tetragonal. It's diffusionless. And if that concentration is above 0.158% carbon, that's critical. If you don't have at least 0.15% carbon, you can't form martensite because you just don't have the carbon to load up into that body-centered tetragonal crystal structure. So there's very few slip planes in body-centered tetragonal. There's very few slip systems. That means it's very hard and very brittle. So when you quench something to form that martensite, you have a very hard material, but it's very brittle and easy to break. Tempering gets you back to a balance of materials, but keeps some of the advantages of martensite. So you have some martensite. Now, the curves go much differently when you have phase transformations of alloys and how all of this will work. So the effects of adding in other elements and changing these materials the way that you do is by changing the transition temperature, and these alloying elements do that. So these materials, chrome, nickel, molybdenum, silicon, manganese, they all slow or retard the transition from austenite to alpha and cementite or iron carbide. This reaction and the formation of perlite and bainite are keys to the process. So when you add in these alloying elements, eutectoid temperature 727 still, you add these in. This region is austenite. Martensite below about 270, 280. You get alpha and bainite at this region. You have perlite up at this region. But again, you're talking single second to get really down into the martensite range. 10 seconds gets you some bainite, some martensite. These phases change how this reacts. So it changes the shape of some of these curves. There's also continuous cooling that shifts some things. So there's a conversion that happens for this continuous cooling in the transformation diagram that becomes it shifts the curve a little bit. So as you continuously cool, this would be your cooling curve for something like air cooling over the course of time. Comes down from 800 and it comes down a little more reasonably. The isothermal heat treatment is a process that you guys are going to be doing in another one of the labs to heat treat a metal that has sufficient carbon percent. So 0.458% carbon. It's an iron carbon alloy. And we want to sketch and label the time temperature paths to produce 42% proeutectoid ferrite and 58% coarse pearlite. The second case, a 50-50 of fine pearlite and bainite. Third case, 100% martensite. A fourth case, 50% martensite, 50% austenite. So all of these are starting from the same weight percent carbon. The only thing we're changing is how quickly we're cooling to what temperatures. So what does that look like? For the first one, a 42% proeutectoid, 58% coarse pearlite. We would have to isothermally treat at 680 C so that all of the austenite transforms to proeutectoid alpha and coarse pearlite. So the pearlites, we show weight fraction of pearlite of 0.58, weight fraction of our alpha, our ferrite, is 0.42. For the 50% fine pearlite and fine bainite, you hit this transition line. So you isothermally treat at 590, and then you isothermally treat at 470 C. So that brings us down into this region. So all the remaining austenite transforms into bainite. 100% martensite, you have to get down within less than a second below 200. So you have to rapidly quench to room temperature. And the 50-50 martensite and austenite, you have to still quench to 290 and hold the 290 temperature in order to get all of the grains to grow specifically how you want them to. So what mechanical properties change and how do they change? The influence of the carbon content matters tremendously. So you have the pearlite that's medium strong. You have the ferrite that's very soft. So the hypoeutectoid below 0.76 weight percent carbon. Tends to have a tensile strength as a function of the weight percent carbon. The hypoeutectoid below hypoeutectic below hypoeutectoid below the eutectoid. As that weight percent increases, the tensile strength tremendously increases. So a hypereutectoid is considerably stronger than a hypoeutectoid. It's also considerably harder than a hypoeutectoid. So more carbon, more tensile strength, more hardness to a point. The impact energy and the ductility. So the ductility is in blue. More carbon, less ductile. That's the cost trade. You can't have high hardness, high tensile strength, high ductility. You can't have all the things all at the same time. Hypereutectoid, especially, very brittle, very low in terms of flexibility, very low impact energy, very hard materials, very brittle, can't absorb a lot of energy. Highly ductile materials absorb a lot of energy, deforming the metal. So this is why in crash structures we want ductile metal. In cutting edges we want brittle metal, because those tend to give us the hardness properties that we need to do the cutting job, where we don't want flexibility. It's very important all of those things go together. So the increase in carbon content, both tensile strength and yield strength increase. So those are good. But the ductility decreases. It's always the cost trade. Fine pearlite versus coarse pearlite and spheroidite. The Brinell hardness goes up with carbon for all of them. Fine pearlite is much, much harder than the coarse pearlite or spheroidite. Spheroidite, that makes sense because the grain boundaries are almost ball-like and they are able to sort of slip past each other more easily. Fine pearlite, you really can't have that to the same degree. Coarse pearlite, it's easier to move some of the big grains around and shift them a little bit than it is fine pearlite. Fine pearlite, there's not a lot of movement at those grain boundaries, and that's why they are harder to move the grains around. That ductility is the inverse. So spheroidite is always high in ductility, regardless of the alloy, compared to fine pearlite. So they're always going to be polar opposites. So the hardness goes fine, coarse, spheroidite. The percent retention of, or percent reduction in area as it's stressed in tension is fine is less than coarse is less than spheroidite. So it goes the opposite direction. Always the ductility, percent reduction in area, is opposite of the hardness. So you can't have a hard material that's also ductile. It doesn't work. You can have a hard material on the outside and a ductile material on the inside by having layers of different materials. And that's why we do composites of things. So fine pearlite versus martensite. Martensite is significantly harder than fine pearlite. This is why it's desirable for cutting edges. But it's extremely brittle. So tempering martensite is important to get the desired mechanical properties so that it's not just brittle and you don't touch it to a surface and it explodes. So the tempered martensite is considerably less brittle than normal martensite. It reduces the internal stresses caused by quenching because the material suddenly has to change shape, suddenly has to change geometry, suddenly has to change phase, causing a lot of stress to be built up in the material. That stress internally is reduced, so it behaves less brittle and less explosively as a cutting edge by this process. So the temperature, as that increases, the restoration of ductility is significant. So 40% at a tempering temperature over 600 C, you get most of the ductility back, but also the tensile strength drops precipitously. So from like 1840 probably down to almost 1,000 megapascals in tensile strength. Your yield strength drops proportional to tensile strength for reasons that we've understood elsewhere. So slow cooling from austenite can get you to pearlite. A moderate cooling can get you to bainite, that are long carbide particles. A rapid quench can get you to martensite, which is different phase altogether, different crystalline process. Then you reheat to temper the martensite to get very fine particles, and then it becomes hard to compress. So in terms of strength, martensite's at the top, Spheroidite is at the bottom. Ductility is the opposite direction. So bainite and pearlite are sort of in the middle there. Tempered martensite is typically what you go to get a good cutting edge. So you get a little bit of ductility, but a very hard cutting edge. You wouldn't want to make tooling out of spheroidite grains because they wouldn't hold up very well. So this covers at least this portion of the chapter. We're going to jump to the next one because 11 ties in with sort of the rest of this and brings it to a meaningful conclusion. So this chapter gets into, okay, great, we can talk about martensite and cementite until we're all babbling like Homer Simpson, but what does all that gibberish mean? This is where the actual application comes into play. So how do we classify and deal with some of these things? What are some of the common fabrication techniques? How does all of this work? What are some of the heat treatment processes? How do we improve the mechanical properties of ferrous and non-ferrous alloys? How does all of this work together, especially if it's supposed to work together for the good of all the materials here? So, classifications for metal alloys is important because we need the metal alloys. We have ferrous and non-ferrous, meaning iron containing, so steels, cast irons, and we have other non-ferrous alloys, so non-iron alloys. So again, that cast iron range from about 3 to about 4.5 weight percent carbon. Steels are typically below 1.5 weight percent. It's 1.4 weight percent carbons. So high carbon steel is the region in between those. So high carbon steel or a high alloy is going to be above about 1.4 weight percent. So really not a lot of carbon to get us to a heat treatable steel from the very soft iron that we would have otherwise. And a little more carbon gets us into the very brittle iron of cast iron. So a lot of things change at that point. So a plain or low carbon steel, no additional ions, no additional alloys, 1010, completely non-hardenable, very low tensile strength, very ductile. So something like sheet steel, automotive application, those sorts of things. Structural sheet steel, something that's very soft, doesn't have to be extremely strong. It's going to take a ton of energy on impact because it has very low tensile strength, very high ductility. That's a good thing to have. So a low alloy steel, like a 4310, is going to be things like bridges, towers, pressure vessels, so structural components, things that are more resistant to corrosion, that are low alloys, are sort of hardenable. They are medium in their tensile strength, and they're good in their ductility, allowing some flex, some stretch in the material, because you don't want bridges and towers and things to fail catastrophically. That would be bad. So the medium carbon is another example of a low alloy. The plain, so medium carbon plain, something like a 1040, 0.4% is what that would represent. 0.4% carbon. So the last two numbers indicate the percent carbon. So 0.1% for the 1010 and 4310. The 1040 is a plain steel with 0.4% carbon. So it is hardenable. It has a high tensile strength. It is medium in the ductility. So things like crankshafts, bolts, hammers, blades, 1040 is a reasonable application for that. Heat treatable is something more like a 4340. So 40, the 43 indicates a higher, indicates the presence of other additions. So chrome, nickel, molybdenum, things like that. 4340 is very common for pistons, gears, connecting rods, things like that, things that are wear applications, things that need to be very hard, very resistant. So they're very high in hardenability, very high in tensile strength, very low in ductility. So things that can't take a lot of impact abuse exactly, but they're very high in terms of tensile strength. They're also very good in compression as a result of that. So you'll see a lot of internal engine parts made of 4340 steel. Higher carbon, such as something like a 1095. So no additional elements. High in hardenability, mid-range in terms of tensile strength, poor in terms of ductility, good in a wear application, but no real corrosion resistance. So it's prone to corrosion. So it has to be in a wear application where there's good lubrication to help prevent surface oxidation. Tooling steels. This is where you get up into the upper range. So above above that like 0.9% carbon gets into the tooling steels. So 4190 would be an example of a combination of chrome, vanadium, molybdenum, tungsten, and some different specifics in there. Extremely high in hardenability, very high tensile strength, very low ductility, so very brittle typically for these tools, especially cutting tools. But they do their job very well. So drills, saws, dies, things that have to have extremely high kind of wear, but effectively have to do a lot of processing and those sorts of things. So there's a lot of details there. So there's a lot going on. So stainless is typically above that. And the stainless steels are going to have a lot of information about them. Their composition changes rather widely. These are considered high alloys, so very good thermal properties, typically high temperature applications, furnaces, turbines, very corrosion resistant, some medical applications. There's some other materials that we use preferentially, so it's not all just stainless, but there's some other biomaterials that are used. So very corrosion resistance, very high resistance to high temperature applications, and that's why there's a lot of building codes that require a certain grade of stainless to be used when there's going to be a high heat generation to provide safety. So increasing strength decreases ductility. So we see that cost trade over and over and over again, which is why it's important to understand how this all works. So starting from ore, they add in iron ore, limestone, and coke or carbon, which is then dumped into this refractory vessel. It's held at a very high temperature. The layers of coke and iron ore get stacked. There's some amount of air that gets blown in, there's slag that comes off, and then there's molten iron that reaches the base where the highest temperature is. So the heat generation takes carbon and oxygen, forms CO2. The iron ore, starting at CO2 and carbon, go to carbon monoxide, and the iron oxide become iron and CO2. And the purification happens as a result of that calcium carbonate, the limestone, that combines, or that decomposes to calcium oxide and CO2. The calcium oxide, the silica from the sand, the SiO2, and the alumina come off as slag. So those are the impurities that come off of that process. So steels and cast irons are these iron-based alloys. And the nomenclature, so that you can identify the way that these work, is this 10 series is a plain carbon steel. An 11 series is a plain carbon steel that's resulfurized to allow easier machinability. A 15 series is about 1 to 1.65%. A 40 series, that's a 15 is manganese. 40 series is molybdenum. 43 series is nickel, chromium, molybdenum. So a chromoly steel is going to be more like a 43, and typically you're going to find it in a 4340. Sometimes you'll find 4330, but 4340 is a very common material. It's known and battle tested in a lot of harsh applications. 44 is a 0.5% molybdenum. So this gives you a range. So it's not a fixed amount exactly. So one person's or one company's 4340 is not going to be exactly the same as 4340 from another company, but they're going to be pretty close in terms of overall properties. So the two X's are the weight percent carbon times 100%. 1060 is a plain carbon steel with 0.6 weight percent carbon. Stainless steels are above 11% chromium. So this gives you the kind of gambit of what those materials are. So you'll use some examples of some 10s and some 40 series steels in the hardenability lab to give you a general concept of what's out there. The ferrous alloys are greater than 2.1% carbon, usually like 3 to 4.5%, are low melting and therefore easy to cast, and they're generally very brittle. Those are the cast irons. So a lot of big heavy tooling, a lot of big heavy equipment, sometimes presses of different varieties, some anvils, a lot of cast heavy equipment, vices, and sort of a lot of the tools filling up Harbor Freight. There's a lot of cast irons in there. Brittle, it's strong enough to do the job, but if you were to just drop it from a rooftop or something, you're going to break them because they're pretty brittle. The cementite decomposes to ferrite and graphite, and that's why when you do break one of those, you'll find that your hands get really covered very quickly in graphite because there's a large amount of graphite present in those cast irons. Especially the cheaper they are, the more graphite you'll tend to find. So generally that's a slow process for the decomposition from ferrite to ferrite and graphite from iron carbide. But the equilibrium diagram we can see here as you go all the way up to 90 and 100 weight percent carbon. There's liquid and graphite on the other side of that 6.7%. And this is why we don't spend a lot of time including the entirety of the range. Is you get, for these larger carbon values, you get a combination of liquid and graphite, austenite and graphite, alpha and graphite. So usually graphite formation is promoted in the presence of silicon. Silicon very often is at least present or transferred in the casting process, because silica is the primary ingredient of the sand that's used in the packing of the molds for casting. So slow cooling rates also promote formation of graphite. So gray iron has these graphite flakes. It's weak and very brittle in tension, so you pull really hard on it. It's stronger in compression, so that's why in something like a vise, cast iron makes a lot of sense, because you got a lot of compression, not a lot of tension going on. Excellent vibrational damping. This would be a poor material to make a slide hammer out of. It'd be a great material to make something like a press out of, or an arbor plate that goes on a press. It's typically going to be a cast iron, something that's expected to have large compressive loads. This kind of gray iron, very wear resistant, very good at vibrational dampening. So it's used in a lot of feet and housings for big heavy equipment. Ductile iron adds some magnesium or beryllium. Graphite nodules form rather than flakes, so they're round as seen in the image here. And the matrix of perlite is a lot stronger, but less ductile than you would see in other materials. White iron is less than 1% silicon by weight. It's a combination of perlite and cementite. It's very hard and extremely brittle. So you won't see a lot of applications for white iron, probably. Malleable iron is heat treat white iron at 800 to 900 C, sufficient that you get graphite rosettes. You get sort of some strength and some ductility. So it's still not going to be ductile like steel, but it's going to be a little better. And then you have compacted graphite iron. So this is relatively high thermal conductivity, good resistance to thermal shock, lower oxidation at elevated temperatures. So compacted graphite iron is more like what you're going to see in cookware because of those particular properties. So something that's been, you can think of it as like a cast that's also being pressed at the same time. You're going to have better thermal conductivity, better resistance to thermal shock. So all of those properties make it much better for cookware. So Lodge cookware is going to be more like your compacted graphite iron than anything else. And the production of cast irons looks something like you have a pearlitic phase. You reheat and hold at 700 C for 30 hours or more. You fast cool it to get perlite and graphite. You slow cool it to get ferritic iron. So you have alpha, ferrite, and graphite. Then you have the white irons. So they come a little higher up. You get a fast cooling will give you perlite and cementite. Moderate cooling, perlite with some graphite flakes. Slow cooling will give you alpha with graphite flakes, bigger graphite flakes. Then You can get perlitic ductile cast iron from a little higher concentration, adding in some magnesium or ceruleum to increase granulation. You'll get perlitic ductile cast iron. Moderate cooling will be perlite and graphite nodules, and slow cooling will give you ferritic ductile cast iron, so alpha and graphite nodules. So the commercial cast iron range is anywhere in this range. So some of the limitations here are high densities and low electrical conductivities, as well as generally poor corrosion resistance. And that tends to be fairly common for a lot of things. So non-ferrous alloys, copper, things like brass, bronze, copper beryllium, precipitation hardened. Brass has zinc as a substitute for impurity, so this is common for things like costume jewelry, coins. It's good for corrosion resistance. Helps the copper not to oxidize so quickly. Bronze, used for a lot of things, for a lot of areas, bushings and harsh environments, high surface hardness, but softer than typically the steel that's riding in it. That's why it makes good bushings. Copper beryllium, precipitation hardened for strength. We talked about precipitation a little bit. Titanium alloys, low density, so they're lightweight, versus 7.9 for steel, so they can be a lot lighter than steel. But they're reactive at high temperatures, very hard to weld, very dangerous. A lot of space applications, as well as naval and military, but some medical as well. But because the titaniums are often softer than steel, they tend to be not great for structural applications. So they're not really ideal at load bearing necessarily. Aluminum alloys, very low densities, lower than titanium, significantly lower than steel, 2.7 gram per cubic centimeter versus 7.9 for steel. So significantly lighter, almost a third. Copper, magnesium, silicon, manganese, and zinc are common additions. They're solid solutions or precipitation strengthened, things like structural aircraft parts and packing, to make very strong materials, almost like a mild steel, but with a third of the density. The obvious appeal in the case of airplanes and aircraft parts is to make them extremely strong, but not have them, like magnesium, ignite so easily and not be so brittle. So they are used in aircraft applications. They are used in things that are designed to explode or catch fire on purpose, because that tends to work really well. So you can use that easy ignition as part of your design parameters for things designed to be munitions. Refractory metals, high melting temperatures, niobium, molybdenum, tungsten, tantalum. Those are refractory. They are much different in their applications. Because they're high melting temperatures, they make good things like filaments for bulbs and things of that nature. And then finally, there's noble metals, gold, silver, platinum. So these are oxidation and corrosion resistant, and they lend those properties to things that are alloyed with them. They just don't always like to be alloyed because they don't like to play along with other materials all the time. So how do we fabricate metals? We've seen a lot of instances from our young British blacksmith. The idea of forging material, cast molten metal into a mold is fairly common. We've seen how some rough stock is formed to a final shape using forming operations through dies and things, especially in the case of hot working. So a lot of hammer forging and things are on the hot working side. Sometimes cold working, but mostly we're doing hot working in those. And therefore, there's deformation temperature that has to be high enough to cause recrystallization and allow for large deformation, versus cold working is below the recrystallization temperature, strain hardening occurs, and they're very small deformations. So cold working is pounding something with a hammer. Hot working is heating something and then pounding it with something like a hammer to create large movements, large deformations in the material. So there's a big difference between those. Some of these methods, including in the forming side, are hammering and stamping. We've seen some of these examples where you have a blank, you have a die, the force is applied, and it smashes the material into that geometry. You have rolling, hot or cold, depending. So these I-beams, rails, sheets, plates, all sorts of things are hot or cold rolled, depending. Drawing runs it through the die. So we've seen some of those examples. And extrusion, where you're forcing a billet through a die in order to get to a specific new geometry. So dies are really key. So things like wrenches, crankshafts are forcibly stamped or hammered into place. A lot of internal parts for engines can be formed. I-beams, rails, we've seen examples of those. Sheets and plates, we've seen examples of those, typically by rolling. Drawing are things like rods, wires, and tubing. We haven't seen a lot of examples of those, but dies have to be well lubricated and clean to be able to operate. Extrusion, meaning rods and tubing mostly. You have the ram and you shove the billet through the die. And then you have a pretty strong die holder. Casting, we haven't seen lots and lots of examples of, but we've seen a couple. So that gives you, again, the context to fill in the rest of this information. So the mold is filled with molten metal. The metal is melted in a furnace, and there's sometimes alloying elements added. Then there's common, it's an inexpensive method, so it's typically not tons of machine work to make a casting. Sometimes there's machine work after the casting, but the casting is an inexpensive way to make the part compared to machining it from a billet, which costs considerably more time, energy, and effort. Then it gives you good reproduction of broad shapes. It makes for a weaker product than something machined out of a solid billet. And there can be internal defects from the mold. So it's a good option for materials that are brittle and won't take well to machining. It's also a good option if you're trying to make something inexpensively and do the bulk of the product development in a casting single operation rather than trying to get all of those features with another kind of processing operation. So the sand casting typically has, especially for large parts like engine blocks, casting makes by far the most sense rather than some other options that would be many more times time intensive. So the best material to be able to withstand temperatures in excess of 1600 C, inexpensive and easy to mold, sand, and that's why sand with the right amount of oils and other things to create a mold pack is what we tend to use for these. So you have sand, you have the molten metal, you have a sprue and a vent on either side. There's also investment casting, which is for low volume complex shapes, things like jewelry and turbine blades. So you have a mold formed by pouring plaster around some kind of wax Could also be plastic, so 3D printed material and things like that have been used for this a lot more recently. The plaster is allowed to harden. Then the wax is melted, or the plastic is melted out of the plaster, and a hollow mold cavity remains. And then the molten metal is poured in and allowed to solidify. There's also die casting, so high volume for alloys having low melting temperatures. So almost all metal children's toys are made with some variation of this. So you have a molten metal, pot metal, whatever scraps they can find around. And it fills the cavity. Continuous casting can have a funnel of material, like rectangular slabs and cylinders. I haven't seen a lot of examples of that in practice, so I wouldn't know how to tell you where that would look, or where to look for that kind of end application. Powder metallurgy. This is becoming a more common technique. Fill a mold with powder under pressure. You have a point of contact. You sinter them, densifying by diffusion at higher temperature. Those metals come together. They're often called MIMD parts. Metal injection molded is essentially what this is trying to get to. There's also welding for the fabrication methods. This is another one you guys are going to do in practice in one of the labs, where you're going to work on putting two pieces of metal together with the amazing glue that is welding. So you have a filler metal, you have the base metal that's melts, you have the fused base metal, and you have the heat affected zone around that. The heat affected zone is a region where that microstructure has been altered because of the changes in temperature. So we've just seen how that looks in terms of the way that the phase diagram, you change temperature, you change the path that it takes, and it continues along a certain isotherm or along a certain cooling curve, and you get different microstructure from the bulk of the material, from the piece 1 or piece 2, the unaffected areas. So that heat affected zone is always weaker than the original material was. The thermal processing of metals, this has a lot that goes into it. So annealing is common in order to reduce the stress, the built up stresses from plastic deformation, from whatever operations have happened, non-uniform cooling, phase transformations. Spheroidizing steels makes it soft and good for machining. Heat treating just before the eutectoid held for very long time frames, 15 to 25 hours. Full annealing makes steels good for forming, so heating to get to austenite, and then furnace cool to obtain coarse pearlite to get a full anneal. Normalizing the steel, so this is deforming the steel with large grains, heat treating it to allow recrystallization and formation of the smaller grains. That can be important for machining operations. Process annealing negates the effects of cold working by recovery or crystallization. So the process annealing is often done in the middle of making something in order to continue forming the steel and keeping it easy in terms of wear on the equipment, so you're not just work hardening or cold hardening, cold working the material into a material that you can't continue. So full annealing looks like this. So full annealing curve. So you furnace cool it slowly over the long course of time. Quenching, you rapidly drop the temperature precipitously. Tempering then brings the temperature up for a little while to allow some recrystallization, and then tempering your martensite. So another one that you guys will do this semester is the Geometry end quench test for hardenability. So you'll measure the ability to form martensite by the end quench test. You take a specimen, you heat it to the austenite phase, so heat it up over 800 C. Then you drop it down into this holder and you hit it with water at room temperature, and it cools, and the distance from the quenched end has a lower and lower hardness, and you'll see some kind of a curve that comes out of the data that you get from that lab testing for Rockwell hardness on the C scale. Why that hardness changes with distance is that the cooling rate decreases from the quenched end. So the hardness is going to be highest at the quenched end. It's going to drop pretty quickly and then be kind of linear as you get farther away from the quenched end. So if you're doing an isothermal transformation, you'll see that there is martensite formed in this process. But it takes a little while for it to reach the martensite level because there's an austenite martensite combo. If it starts to, as it gets farther away from the end, it quickly starts to include martensite and perlite together. Farther up, you get fine perlite. Farther up, you get just coarse perlite, and that's much softer than the martensite formed originally at the end. So as you change the alloy, you can change the hardenability of how each of these works, and that allows for the cooling curves to have a few different things all together. So the hardenability curves for these 5 alloys, starting with 1040, going up to 4340, the hardness for 4340 is consistent. The hardness for 1040 varies rather dramatically, with 4140 kind of being in between those two. So each of these has 0.4% carbon, but the degree to which they are alloyed changes greatly the hardenability of the material. So the 4340 is going to be a hard material no matter what you do to it. The others are going to change radically depending on how you've treated them in the processing. So those are tunable, where 4340 is pretty consistent. So each of these 4140, 4340, 5140, 8640 have nickel, chrome, and molybdenum, and they shift the nose to a little bit longer times from A to B. So they shift the curve to the right, giving you more time to form martensite. So it's easier to form, doesn't have to be quenched as quickly. So that quench medium changes. So air is a really low severity quench, low hardness. Oil is a moderate quench method with moderate hardness. Water is a high quench with a high hardness. So the geometry is also a factor. When the surface area to volume ratio increases, the cooling rate through the interior increases, and the hardness throughout the interior increases. So the center has a low cooling rate, low hardness. Surface has a high cooling rate, high hardness, especially in the case of the Geometry end quench test. So the precipitation hardening that we've seen some examples of we've got a lot that happens in this process. We've seen what that does in terms of the particles impeding dislocation motion. The aluminum copper system is an example we'll look at here. So you have a heat treat to get alpha. So you cool from a little over 500 C. So you raise the temperature to 500 C and quench it to room temperature. You retain alpha as a solid solution. You reheat to nucleate small particles within the alpha phase. So you reheat to a lower temperature. And the other alloys that are going to precipitation harden would be like copper beryllium, copper tin, magnesium aluminum. And the composition is going to vary widely. So we're going to look at the effects of precipitation heat treatment on tensile strength and ductility here a little bit later, but this at least gives you a pretty good range. This is a lot of information, and that's very quick at this point in time to kind of be turned into mush on all the terms. So we'll cut this one a little bit short and give you guys a reasonable pickup point for the next one.